It's so easy.
I
with
know, it's
half the room.
darn weather.
All right. Hello, everybody. Thanks for coming out. It's raining. We really appreciate you being here. Sorry, getting situated. All right. Hello. My name is Aaron. This is Michael. Erica's down here. We got Adam and Brian running the show. Jasmine and Caleb, you're going to see them later. Do some astronomy in the news. Sam is ETA on his way. There's traffic from coming from Bernie, and so we had to switch the slides around. He was supposed to go first. Now he's going second. Sam makes weird choices. I don't know. Okay. Yeah. So welcome to Astronomy on Tap. How many? I see a lot of familiar faces. Is there anyone here for the first time tonight? Cool. Thanks for coming out. Sweet.
Welcome.
That's a good crowd.
It's usually more crowded than this.
Yeah. Usually it takes us like 5 minutes to calm the crowd, but this is really quick because it's not that loud. For the first timers out here tonight, I did my intro. I did all that stuff. Yeah. For the first timers, Michael, what is Astronomy on Tap?
Well, we are a worldwide phenomenon with locations all across the globe, most in the United States and Europe, but you see we have others in other places. Our Astronomy on Tap has been here since 2017, so this is our 8th year now in operation. We're very happy about it. As you saw, this is our 56th event in person. That's right. We had like 10 virtuals during COVID, so we've had more than 60 events total. Yes, and so this is all of them, and it's a fun network. Sometimes we'll get to meet some of the people, especially the HQ people will go to scientific conferences to spread the word about what we do and try to encourage other scientists in cities that don't have these yet to start a new one. And I was very happy because just this past few months, a new one started in Ithaca, New York. So it was really, really cool to see that. But what makes ours special? All above the rest. Well, we're interesting. As you see, we'll have 2 interesting talks tonight, both with very different but similar topics, but different approaches. As we'll see, one is more engineering and one is more science. Fun. We love to give out prizes. So we do trivia at the end, and today's prizes will feature, we always have some stickers, and we'll have probably some posters and Celestron stuff. Frisbee, there you go. Yes, so if you're a Celestron fan, we've got you covered. And interactive, most importantly interactive, because we will give you all the opportunity to ask our speakers questions. And given the turnout tonight, if you text in, you'll probably have your question read. So if you have a burning question, text it into the number. It'll be on the slides later on. And please interact with the speaker. They're happy to answer any of your questions. I don't know what.
Sam started a new segment apparently. Send your pictures in, and this is from Lee Childers. He spoke a couple months ago, and he took this out at Big Bend, the Lagoon Nebula, and so that's our background for
beautiful
today.
Yes, so if you go somewhere and you take a pretty picture, please feel free to send it our way, and we'll feature it right here. As you see, you don't have to, I mean, this is Big Bend, but you don't even have to go too far. As Caleb can tell you, they go often to South Yano, which is just less than 2 hours away, and they get some beautiful pictures. So it doesn't take a lot of effort to get pretty pictures of the sky. All right, tonight's program, we're going to be, like Aaron said, we're flipping it around. So we'll start with Mr. Trent Peterson, who will be talking about assembling a punch WFI. We will have our break, and then the Astronomy in the News presented by Caleb Guimar and Jasmine Singh. And then our second talk will be our very own Dr. Samuel Hart, who will talk about, is the sun running out of helium-3? And why should we care? He'll tell us about that. And then our totally normal trivia to round off the night. One thing that wasn't on one of the slides that I did forget to mention that, especially because there's a lot of new people here. If you are interested in keeping up with us, we do have socials. We're on Facebook. We're on Insta. We're on the Twitter and the butterfly, Blue Sky. We have a website and we have a YouTube. So there's a lot of ways to keep in touch with us. So please look out for those. AOT SATX is our handle. And we also have a mailing list, which will be, I think the QR code comes up during the break. So if you're interested in returning and being part of one of the more robust crowds, come back. But get started for the evening. Oh yeah, there's the text line for tonight.
Usually we have it up on the second TV, but we only have one laptop running today. So if you want to note that down, get it ready to go or not, it'll come up later. But that'll be the text line. Don't be weird. And I'll do Trent. All right. All right. Mr. Trent Peterson graduated with a physics degree from the University of Texas at Austin. Trent Peterson is currently a senior engineering technologist at Southwest Research Institute here in San Antonio. Work includes assembling instruments and payloads for spacecrafts and clean room infrastructure. Recent missions. That's a good one. Recent missions include Punch, Scorpio, LMS, Mini Find, or Mini FND? Mini FND, APSR, and more. All right, let's give it over for Mr. Trent Peterson. All right, and then for the first timers out here tonight, we have a drinking word. Pretty self-explanatory. You hear the word, and what do we do, everybody? Woo! Hey, take a drink. Drive responsibly. What is the drinking word?
It'll be on the first slide, but it is WIFI, which is the WFI. All right, so we're going to talk about assembling a punch WIFI. So I recognize a few of you out here tonight that I may work with even, but for those who don't know me, Trent Peterson. I work at Southwest Research Institute, senior engineering technologist in the Space Science Division. And so like I said, today's drinking word. I'm not going to say it again yet. So a brief overview of the Punch mission, okay? So it's a perimeter to unify the corona and heliosphere. It's a constellation of 4 spacecraft. There are 3 wide-field imagers, which is WIFI, and 1 near-field imager. The mission is to study the sun's outer atmosphere, the corona, from where it transitions from being the sun to solar flares. So it's kind of solar winds, space weather, things of that nature. It was successfully launched earlier this March on a SpaceX Falcon 9, and it's up there taking science data now. So any of these projects start off with an engineering and design phase. So you get your scientists together, your engineers to come up with the idea, they flush everything out, you start coming up with models, drawings, start fabricating parts, you do an engineering model, the whole works, and they get all that figured out. So here we kind of have a cross-sectional area of what the instrument looks like itself. So in the front, we have a solar baffle, and that consists of 6 knife edges, and each one is 1/1000th inch shorter than the next one. And what that does, it helps when you're looking at the sun, it helps the vignetting, so you get a much crisper image when you're looking at the sun. Light then goes into the baffle assembly, which is painted with this black optical paint, so we can deal with all the scattered light. And then here, we've got the pupil, the entrance pupil. Behind it, we have a polarizing wheel. So we've actually got a couple different filters and polarizers in there that we can rotate through depending on what kind of data we're trying to acquire. And then lastly, on the back end, we have our camera, which we have a CCD inside there. And, sorry, forgot to mention too, in between that, there's an optical lens stack. So we've got actually 8 lenses in a very tight package. And that was a very complicated piece, and I'll talk about that part in a moment. So from here, you have all your parts fabricated, right? You do all your inspections, and then you start to gather them, all right? So we have a thing at SWIRI called control stores. All of our parts go there after all of their inspections. Everything's tracked, everything's serialized, everything's known. So everything that goes into these instruments, like this Wi-Fi, has its provenance and has all of its tracking. Another example, all of our parts come in bags with QR codes. Everything is tracked. You want to know exactly what you're putting in that thing. You don't want to have failures or any surprises. And then here is our CCD assembly. Very delicate and expensive, but they're fun to work with. Oh, wrong direction. Okay. So once you get all your parts, you clean them all, and you take them into the clean room. So I work a lot in the clean room, and it's a quite involved gowning experience, right? You're doing the full thing: hoods, boots, jackets, everything. And this was actually an accidental photograph. I was trying to take an inspection picture of some work I just done. Realized my cell phone was on selfie mode, and we were looking at it, going, "Hey, this is kind of like a Wi-Fi bird's eye view of what the instrument sees." So I was like, "Man, we got to keep that. That's just fun." And so that's me and one of the engineers and one of our other technicians. And we can see a camera assembly starting to get put together here. Whoop, I keep going to go the wrong direction. So more photographs of actually working on the parts. So we've got our detector out here, very delicate, lots of no-touch surfaces. If you look at these things the wrong way, it's over, right? So you definitely can't touch the purple part. You can't touch the silver part. There's tiny little bond wires in there that are like the size of your hair. You can't bend those or break those. You might notice all this gray stuff. Well, that's glue. It turns out we fly a lot of glue in space, a lot of tape in space, and a lot of space zip ties, which is something I never realized until I started doing space. So we're like, man, there's a lot of tape up in the around the Earth and on different missions. But it's space tape and space glue, so it's legit. And so we have to make sure that all of our fasteners get glued, everything. You can't have anything loose or rattling. And then here we've got the baffle assembly all prepared, ready to accept a camera and a lens stack and a polarizing filter reel here. That's all black optical absorbing paint, which you also can't touch. So it's very difficult when you build some of this stuff, because you're like, how do you actually assemble it if I can't touch it? So you have to have a lot of cool jigs and a lot of good strategy on not messing things up. So this particular lens stack gave us a lot of trouble. So we received them like this as a completed unit. We went to test them, and some lenses started rattling inside of them, which is not a great thing because we have a very tight tolerance on this lens stack. We're going from a very wide field of view, and we've got to take it down in a very short distance to a small kind of 1.5 inch by 1.5 inch detector while keeping the optical resolution good. So there's 8 lenses in there, very tightly packed, tight tolerance. So that's not great. So we had to take it apart. And you can see, actually, these are some of the lenses stacked here with their spacers. And it was a very kind of scary game of Jenga, because you have these lenses, they're tiny. You got to, one, make sure to get them in the right order, too, right? Second of all, some of the faces look similar on both sides, so you're holding them going, okay, wait, is this the convex side or is this the other convex side? Well, you have to get it right. And so what I would do is I would assemble them, and we would hand them over to the science team. We'd mount them onto a camera. They'd run all of their image checks, make sure the quality's still good. And then at that point, we modified the housing, cut these grooves, and then I glued them in place. And we glued them in place after we checked them, because if I glued them beforehand and they were wrong and found out that I flipped an optic or something, that's not something we can really easily undo. That's a really involved surgery. So thankfully, the glue fixed the problem, and they worked out okay. Okay. So now, after you've got your whole thing assembled, you got to do some initial function testing, right? You got to make sure, hey, does this thing image well? Does the polarizing filter wheel work? Do the temperature sensors run? And one of our really important components on our instrument was this door, okay? We had a one-time open door that was going to protect all those delicate optical features. We didn't want dust and debris getting inside of here on the rocket ride, or when it's transitioning into its orbit to its final location. So we had a mechanism that would open that door. Now, how we accomplished that was with a unit called a HOP, which is a high output paraffin wax operator. Basically, it's a fancy pin puller. So there's a bunch of wax inside this unit. You heat it up, and it'll actually pull a pin that allows us to pull a mechanism and spring open the door. Now, this was a critical aspect to this mission, because if we didn't have a door that opened, then we have no instrument, and Wi-Fi is a failure, and we have We're flying a brick at that point, right? That's a weird woo, isn't it? But anyhow, so every opportunity we would test this door. Every operational test that we do, we test it in all kinds of different vectors, making sure that it would open this way. If we hung it this way, it'd open this way. Because basically, if it worked in a 1G environment in all those ways, it's going to go really well in a 0G environment. There was also a remove before flight pin on that door assembly that we would have when we were working with the unit, but we didn't want to relatch the hop. And so I have had nightmares about not having those pins removed. And so when the guys are on the ground in Vandenberg at the launch site, I'm like, I want pictures of these pins. I want them on my desk. I want to hold them because that guarantees me that they're not there. Because it'd be really, really unfortunate if everything else worked well, but we left the remove before flight pin in. So once you get through initial testing, then you go to the mechanical vibration. Okay, this is your slip table, right? And so basically, we will mount it. Wi-Fi's entombed here in some lumaloy and under nitrogen purge. And the slip table is what you call a mechanical slip table. The engineers will get a profile of the type of load that the instrument's going to see on the rocket, okay? And they input that into the slip table. Sometimes it's thousands of hertz, 14 Gs even. And so you mount your instrument there, and they shake the tar out of it, right? And it's a long 2 minutes. Okay, it's a very long 2 minutes. You just spent a year and a half building this delicate thing, and you're just watching it just shake, right? And so at that point, one thing that I have learned by doing all these vibes is to guarantee you to have a good vibe, you have to take a power stance, okay? And you just look at things, you say, you better not move. You stay where you are, don't. And because you have to threaten the thing. And a lot of times it actually works out pretty well. So after the very long 2 minutes, the engineers go and look at all of the data and say, yeah, okay, things haven't shifted too badly. It looks nice. And then the engineer says, okay, now we have to do what you call an inverted acoustics test. And you say, what is that? Well, that turns out that's a fancy term for pick it up, shake it, and hear if anything rattles, okay? And so here you are taking your multi-million-dollar instrument that you can only hold on 2 or 3 really delicate places, and you're flipping this thing upside down. You're just shaking it, right? And you're thinking, just don't drop this thing, right? And so we don't hear any rattles. It's great. Well, then you remount it in a different orientation because you have to check that axis. And you do that inversion acoustic test again. And then you do it in Z, and you do it again. So you have to have this kind of high intense factor sometimes where you just have to do the work. But sometimes it's a little scary and sometimes it's a little fun. So once you pass your vibe, you make it into thermal vacuum, okay? So this is our big DS9 chamber here, 9-foot diameter vacuum. I believe that's an older project for some hurricane satellites. I forget the name off the top of my head. Cygnus, thank you. Yeah, some of you guys know. And I got a really cool picture of me in the vacuum chamber as we were installing the Wi-Fi. You fit a lot of cool stuff into a pretty small package. So inside this spacecraft bus, you've got solar panels, batteries, avionics flight units. You've got the radios, the control units, readout systems. Everything that you need to kind of operate this observatory is in this package here, including the shiny space blankets too. And once you have attached the instrument onto the spacecraft, you go through vibe again, and you go through 2evac again, because you want to know how these two things interact with each other. Even though they've been tested independently, you got to test them together. So the amount of testing is just absolutely crazy. And so the next round of testing too is you go into an EMI chamber, electromagnetic interference. And so that's a big Faraday cage that we have on site, that you make sure that the radios can talk and that there's not interferences. Can you control the things? Do they produce weird noises that NASA's going to be mad about? All the things, right? And then our latest facility that we have is this acoustic chamber. So we have a room that's 25 feet tall, 16-inch thick concrete walls, and we've got 6 1,500-pound speakers that are capable of producing 150 decibels, okay? And so we line them up and we put our spacecraft in the middle of it. And we blast it. I mean, it's like a thunderous roar. And this is because you would think mechanical vibration is enough, right, on our slip table. However, there's different phenomenon that go on when you have acoustics of a rocket, because you've got an air mass trapped inside there, and you've got the pulsing the engines. So you can imagine when you're driving down the highway and you want to roll your window down, you get all that thump, 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 thump. Imagine that 1,000 times more inside of a rocket. So this thing is capable of producing about the same amount of sound if you were in front of a Falcon 9 at the base of it. So it's quite loud. Also don't want to be in the room when that happens. And so at that point, you box up all your Wi-Fis and your NIFI, and you load them up into a trailer tractor that's white glove delivered. We had 2 engineers that had 28-hour drive to Vandenberg, California. No stops, only for bathroom there. They spent a few weeks integrating them onto the ring here. You can kind of see them all 3 of them here, one's on the other side. It was also a ride share with SphereX, which was pretty cool. And then it launched successfully here. Here's the rocket. And, I don't know what I'm doing here. And we had some really cool pictures of them actually coming off of the fairing and making their way. So they're really nice photographs. So it was a really rewarding moment to see, like, there they go, off to do their mission, and they're behaving, and they're producing quite good science data right now, and hopefully they're up there for many years to come. So thank you.
Awesome. That was cool. All right. First question. How reflective is the black paint that's used?
So I always like to joke, but that's like sucks the photons out of your eyeballs. So when you're trying to do inspections of it, like you have to have the brightest lights, and you have to have really high UV light, because it's just really hard to see. One time many years ago, slightly different paint, but I actually painted a cardboard box with the inside of this black paint. And I dropped something down inside there to pick it up, and I couldn't actually pick it up because your eyes use the reflections to tell how deep something is, and it was just really weird. So very, very non-reflective and very dark.
Follow-up to that, has Vantablack ever been used?
So we haven't used Vantablack, but on those knife edges that I talked about earlier, that was actually an Actar product, which is almost as dark as Vantablack as well. And that was a very expensive thing that we get to ship off to Israel, and they did the Vantablack and came back to us. Also a very delicate no-touch surface. So,
speaking of shipping, how many parts are made in-house, or how many are not made in-house?
So as far as the Wi-Fi instrument itself, a lot of the stuff was made in-house. All those baffle assemblies, the cameras, all the mechanical parts were fabricated, minus the detector, right? We produced that from Teledyne. The lens tube we produced from Teleview.
Oh, really?
And then
Wow.
that's a Teleview lens
Cool.
stack. And then the readout system was from NRL, National Research Laboratory. So a little bit of a partnership, but most of the parts can be fabricated. The big spacecraft baffle, or the big bus itself, was one giant piece of aluminum that we hogged out in our machine shop. So a lot of parts made in-house.
Is Teleview like a widely used, I don't know if contractor is the right word, but like for optics?
I think we were probably one of the first to fly a Teleview, because Teleview is mostly ground-based
Yeah.
telescope stuff. So they were pretty happy to put their stuff on a flight unit. But that was one of the challenges we had, because they hadn't done flight before, so that's why we had to do our modifications.
And it's cool for like, because like I have a Teleview eyepiece, so it's cool like they make optics that go in space. Like,
Yeah,
that's a really
yeah,
cool thing
they
to say.
did.
Can you explain the light shades again?
Which, with the light shades? With
Like the knife edges, like the baffles?
the knife edges? Okay, so you have to forgive me because I don't remember what the actual physical phenomenon is, but so we have these little knife edges that are they're not very wide, right? They're probably like, I don't know, a millimeter or two, and they step down 1/1000th of an inch on the way. There's 6 of them. So what I'm told is when you look at the sun, because we're pointing the sun right at the edge of that knife edge, right? So when the beams come over, you have a lot of vignetting, right? You have a lot of fuzziness right at the edge. That will take away that physical phenomenon. So you can actually get a crisp edge of the sun when you have them this way. So it's a pretty cool phenomenon. Very challenging part to machine from what I understand, because something that thin for that long is hard to warp it. So
Did all 4 components fly in one rocket? If so, how were they separated in orbit to the network, to form the network?
So there were all 4 of them, all float together. So it was a ride or die kind of situation. And they would release 2 at once, and each unit has actually a propulsion unit on it. So we were the first satellites to use a water electrolysis propulsion unit, actually, that would separate the hydrogen and oxygen, and then we'd burn it. So actually, we lost all 4 of them, 2 in like the first minute or so, and then another 30 seconds, the other 2, and then they just would propel them over the next month to their ultimate orbit.
Since there are so many no-touch areas, do you have a plan when you're assembling parts?
Yeah, so sometimes there's a plan, and sometimes there's okay, how are we going to do this? We got to come up with the plan. And so there's a lot of on-the-fly stuff, and there's a lot of phone calls while you're in the clean room going, hey, how do you think we should do this? We shouldn't touch this. But you get creative. You know, sometimes you put a screw down into somewhere and you pick it up that way, or really clean gloves. Sometimes you can touch some stuff, but sometimes you want to avoid it. yeah, it can get creative and get very fun sometimes, and scary too.
I'm not sure if you mentioned it. How hot is the thermal vacuum, or
So-
how hot can it get, or
That's a good question. I know we take stuff regular to 60 C or so. I know we can go to 80 C, maybe even 100 C. I don't remember the capabilities of the chamber itself, but we can go hot enough to where most things in space are going to see, right? If you're like in a direct sun orbit or not in a direct sun orbit. So, and it can go quite cold too.
is there any cool data yet? Any cool findings?
Yeah. Well, so I know there's been preliminary data. They've captured some solar flares and things like that. So they're starting to stitch data together from the 3 observatories with the NIFI. I don't know if there's any necessarily finds yet, but they're producing data, and it's coming down easy from what I understand. At the controls, it's starting to get more and more automated, so the data's just streaming down, and they'll keep reducing it and getting higher and higher signal. So, yeah, they're working.
All right.
So,
That's
yeah.
good. It's good to hear. Let's thank our speaker once again.
Thank you all.
It is just past 7:30. We'll take like I don't know. We'll come back at 7:40. Take a small break. Come back at 7:40 for some astronomy in the news. one stand behind the other when you have the mic on.
Okay. Sorry. So, here we go. For this month's edition of Astronomy News. So, first and foremost, what is going to be in the sky this coming month? Well, you are in for a few treats. There are some things there that you would not be able to see on any other normal occasion. One thing in particular. So, first of all, you are looking at a perfect summertime sky now. Yes, in July you are basically in the midst of summer. This is about mid-month at about 10 o'clock p.m. If you notice down here toward the south, you have the nice dense core of our galaxy, the Milky Way, right there visible. And then if you look a little more toward the upper part of the sky there, almost right overhead, you have the asterism that we call the summer triangle right overhead, the bright stars Vega, Deneb, and Altair, each part of their own constellations. Vega part of Lyra the Lyre, Deneb part of Cygnus the Swan, and Altair part of Aquila the Eagle. If you go over here toward the western half, you still have some of the springtime sky stuff over there. It is setting, of course. Find the Big Dipper asterism, part of the Great Bear constellation. Follow the Arc of the Bear to Arcturus, part of Boötes the herdsman. Spike down to Spica, part of Virgo, right there. And then you have the constellation of Leo the Lion setting over there in the west. Follow the front two stars down from the front of the Dipper to the bright star Regulus that forms the Hart of Leo the Lion, and that will help you navigate your way around the nighttime sky. Now, the only really nice visible planet in the evening time sky right now is the planet Mars. It is over there in Leo, but we are getting farther and farther away from it. We are actually outpacing Mars as we orbit around the sun right now. And as the months go on, Mars will actually wind up getting closer and closer to where the sun is in the sky, and eventually we'll be behind it. So as we get farther from Mars, it'll become a lot smaller in the field of view of a small telescope or a pair of binoculars. So right now, if you look at it, you'll just see kind of a little salmon-colored dot there in the sky. But nonetheless, it is still there for you to see. If you want a few more interesting planets to look at in the nighttime sky, wait until the early morning skies. Around 4 in the morning, both Saturn and Venus are very well placed throughout much of the month. I'll let you do a little more research on that on your own, though, when you get the chance. So, again, the nice Milky Way overhead. Make sure to scan that with a pair of binoculars for some wonderful deep sky sights. And for this month, I have a deep sky challenge for you. It is what you call the North American Nebula, NGC 7000, an H2 region, a cloud of glowing hydrogen gas. It's actually being energized by a large star within the cloud of gas. It's actually hiding behind that dark dust lane there. Nonetheless, though, it is a very, very faint object, so get out underneath extremely dark skies. And in the spirit of the 4th of July, you will, if you use your imagination, find a outline of our wonderful country there in the object there, in the nebulosity there. It's about 2,600 light years away. So again, though, very, very dark skies. Look with binoculars. Just look right off the star Deneb right there in the triangle, just right over there. You'll find the North American Nebula. But again, very, very faint, dark skies. Dark skies are a must on this one. Now for the special object. There is a nova visible in the sky right now. No, it is not the nova that everyone has been waiting for. It is not T Corboreal. It is V462 Lupi. It's down here in the constellation of Lupus. Lupus is supposed to be a wolf. It's this kind of odd shape of stars right here. You are fortunate that you are in the state of Texas right now, because if you're much farther in this state, you would have a very, very hard time finding this. So find, again, dark sky, clear southern horizon. You'll find the constellation of Centaurus, this kind of Y-shaped thing over here. And then if you just look over from Centaurus, there's a couple of small stars in a row there. Look in between those couple of small stars and that star right there with the pair of binoculars. And in the pair of binoculars, you'll see this little triangle shape of stars right here. and then right off the tip of that triangle is a star that is not normally there. It is about the same brightness as the 3 stars in the little triangle. That is this nova that has brightened. Make sure you get a good look at it over the next probably couple weeks or so if you get the chance, because it will dim down as the weeks go on. So limited time to see this absolutely amazing object. And with that, I think we'll go ahead and move on to the astronomy news stuff. So Jasmine, take it away.
All right. So possibly the biggest story, at least in my eyes, that I want to talk about from the past month or so, is that the Vera Rubin Observatory's first images have been revealed. So after over a decade under construction, the Vera Rubin Observatory has released its first images. It is an 8.4 meter telescope, and it's considered, at least right now, the largest digital camera ever built. Over the course of 10 years, it's going to observe and capture approximately 20 billion, with a B, galaxies and find millions of unseen asteroids, comets, and interstellar objects, which is going to help in the realm of planetary defense, should one be on that course towards Earth, which I don't think there will be. So this one is, I say Trifid. I don't know if it's Trifid, Trifid, whatever, but Trifid and Lagoon nebulas, and this one, very beautiful. Obviously, you cannot count by hand, but it contains about 10 million galaxies in this image. I recommend going online and actually looking at these pictures, because we know PowerPoint does not have the best the best image resolution, so you want to see online. And now I want to give a few kind of facts about Vera Rubin, because I don't think people realize just how important and changing, this groundbreaking this observatory is. So each image from Rubin is approximately 3,200 times sharper than a photo from a smartphone, and they're about 6.4 billion pixels each. So we would not be able to see those images with the human eye. You would need about 50 Ultra HD TVs to see images from Rubin at full resolution. Its field of view is absolutely enormous. It's able to capture a chunk of sky about 40 times bigger than the full moon in a single shot, which covers nearly 2% of the entire visible sky at once. It will collect about 20 terabytes of data every single night, which is about 6 to 10 petabytes of data every year. Multiply that by 10. 1,000 times more data than Hubble, 300 times more data than Webb, and it's essentially working to build the largest dynamic map of the universe ever attempted. So it just kind of makes you think like, okay, humanity did that. There's some hope out there for science. So really excited to see what's to come from Vera Rubin. And next, we always have James Webb news, so nothing shocking here, but James Webb has just found its evidence of a Saturn-mass planet using direct imaging. So we have new evidence of a Saturn-mass planet orbiting the young nearby star TWA7. So the planet right here, TWA7b, it sits in a gap between rings of dust surrounding its star, and that's kind of exactly where theories predict that a planet of that size would form and shape the disk. So it's likely that that is a planet. And if that's confirmed, it would be Webb's first direct image discovery and the lightest exoplanet actually seen using the technique of direct imaging. So pretty cool stuff. This is like breaking news. Actually, this happened just yesterday, which is crazy. So we have our discovery of a third interstellar object heading towards the sun. So there's a new object that was found in the solar system headed towards the sun. It seems to have originated from interstellar space due to its kind of strange trajectory. In this image, you can see it right here. That's what they're calling it right now. And it's the third because the only other interstellar objects in the solar system were Oumuamua and this comet. And yesterday, the IAU's Minor Planet Center added the object to their near-Earth object confirmation list. However, it does not have a chance of hitting Earth. I don't know why it's classified as a near-Earth object, but it's in that list. So don't worry, it does not pose a threat to us. It's just visiting. We'll say that. All right.
I wonder if it's going to really visit us.
Come on.
We'll see if Avi Loeb comes up with some interesting explanation for it. Anyway, so a few of the events coming up. Do not miss, on the side of the UTSA Observatory / San Antonio League of Sidewalk Astronomers, as we did last month, we will be doing a series of observings every Friday at 8 p.m. out at the Uvalde County Visitor Center in Conkin, Texas. It's not a half bad place to go observe. It's not perfect, but it is pretty dark out there, and there's a really nice ice cream stand nearby, just so you know. It's a fun place to go observing. So anyway, we'll be out there. If it's not myself, it's usually one of my fellow observers. It's out there as well. So again, keep that on your calendars if you want a good trip out. Our next South Llano River State Park observing gig is on July 26th. We usually start sunset. The last one we did, which was just this past Saturday, beautiful, beautiful, beautiful sky, fantastic evening. If you didn't go, you missed out. If you did go, I know there's a few of you in here, you had a great time, all right? So again, hopefully the weather's great on July 26th, and if it is, I think you'll be in for a really great treat. So, in terms of San Antonio Astronomical Association, every Wednesday at sunset, observing out at Raymond Rimkus Park, and then they have 4 events on the weekends throughout the month. Guadalupe River State Park, July 5th, Kickapoo Cavern State Park, July 12th, Hill Country State Natural Area, July 19th, and Garner State Park, July 26th. So again, some other opportunities to kind of get outside and go to the local parks and see some stars in the sky. And then the Scobie Planetarium will have shows on the 11th, 18th, 25th. No, there will not be shows on the 4th, obviously. And also August 1st, our next Astronomy on Tap will be after that date, so I went ahead and put that up there. And now for the images to close us out.
And we always have to close out with the new images. Sorry.
That may be me.
Okay. So in my Vera Rubin slide, I only included 2 of the new images, but you should really go online and check out the other images. So this one is part of the Virgo cluster from Rubin. Again, very beautiful. Please go online and zoom in. It's absolutely incredible the amount of detail you can see. This one, can't really see it in this lighting, but it is M82, otherwise known as the Cigar Galaxy from JWST in infrared. And this one is a combined image from JWST and the Chandra X-ray Observatory of the Bullet cluster. And what's interesting to note here is that the pink areas are actually glowing X-rays, which can only be seen by Chandra. And then the blue that you can see is actually dark matter, which was it was mapped by astronomers that work on Webb using its detailed imaging. And what's interesting to note is that normally gas, dust, and stars and dark matter are combined into galaxies, but the Bullet cluster is actually unusual because the interstellar gas and dark matter are separated, which offers further evidence in support of dark matter. So that's pretty cool. All right, thank you.
And that is Astronomy in the News. Thank you very much.
All right.
Here you go.
Thank you. All right, our second speaker for tonight is our very own Dr. Samuel Hart. Sam originally hailing from Illinois. He went to undergrad and did his bachelor's in physics at the University of Montana. Go Grizzlies. See his socks. Starting there and then moving here to SWIRI, UTSA Joint Space Physics Program. We started at the same time in 2019. Initially, he worked with the IBEX mission, looking at interstellar energetic neutral atoms, and he fully dove into the heliophysics field. Sam is studying the sun, has been for a while, and one of the most interesting things of his thesis was looking at the helium-3 particle. He graduated last fall, by the way. That's why he's doctor now. And he's been looking at helium-3 particles. So tonight he's going to tell us about these helium-3 particles. And maybe we should be concerned? I don't know. From your title, I'm confused, but he'll tell us all about it. Sam.
Oh, thank you very much. Sorry, wait, can I go? Yeah. There we go. Yeah, this was, sorry, 2 squirrels. This was me in, that's the Alps back there. I was just in France. Very exciting. I'm pretty sure that's a cheap European beer, but you know, when you're in Europe, it's really cool. But that was a fun time. Okay, yeah. Is the sun running out of helium-3? That is a clickbait title. We're really, like classic clickbait, I'm not even going to talk about that. I will a little bit. Oh, my drinking word is puzzling. Okay. So, yeah, puzzling. Please don't say my word. Thank you. Yeah, okay, this squirrel is very scared that the sun is running out of helium-3. So, what's my next slide? Sorry. Okay, there we go. Just need to make sure. Before I get into my research, I'm really going to talk about my research at a lower level. Very interesting stuff. But what do I mean when I say helium-3 that actually is not known by everybody? They often ask me what I'm even studying. So helium-3, well, how do I say this? There are 2 stable helium isotopes, okay? The most common helium isotope is helium-4. It has 2 protons, that is in red here, and then 2 neutrons, which I've colored green. It's called helium-4 because there's 2 protons and 2 neutrons. 2 plus 2 is 4. And now helium-3 is, again, a stable isotope, has 2 protons, which makes it helium, and 1 neutron. So 2 plus 1 is 3. It's helium-3. Now, what's important about these isotopes is that helium-4 makes up almost all of the helium we see in the universe. So 99.99% of all helium is helium-4, and 0.01% is helium-3. So for every 10,000 helium atoms, exactly 1 of them will be helium-3, and the remaining 99,999 will be helium-4. Okay, so what is the composition of the sun? So here we see on the y-axis here, I've got the abundance relative to oxygen, so oxygen's sitting at 1, and on the x-axis here, I have the mass in atomic mass units. So we have, of course, hydrogen makes up most of the sun, and then helium-4 there is about 10% of everything. And then we see helium-3, again, very rare, all the way down here, and it's sitting among all of these much heavier ions, carbon through iron. And then there's also plenty of other elements in the sun, but they're all like way down here. So I just showed the most abundant ones. So again, hydrogen up top, helium-4, 10%, and then everything else has trace amounts of helium-3. So this is the solar abundance. This is what we see through spectral imaging of the solar surface, or the photosphere. There we go. Okay, but I do not study the photosphere because it's cold and lame. I study solar energetic particles, really fast, really bright, and hot stuff. So here's 2 examples of solar or space weather events, or solar energetic particle events. SEP, I might say, because I say it all the time. Oh, okay, well, that movie's just going to keep going. So here's one example of a space weather event. It's called a solar flare. So this is ultraviolet imaging of the sun. So this is very hot gas on the edge of the sun, and then we see this giant solar flare right there. Very bright, rather dangerous if you're out there. If you're a satellite, be careful. And then, oh, I can try it now? Okay, hold on. Let's see it. So the one on the right, which I think might be pulled up in a moment. Here we go. This is a coronal mass ejection. And so we see this is another type of space weather event where we have these. Oh, that happened. Can we play that again? It's going to need like 4 times. Okay, so there's this ejecta that is launched off the side of the sun. So this circle is the sun. And most of them are slow, but when it's really fast, you see all of a sudden you get all this fuzz on the detector. Well, that is actually extremely energetic particles. That thing that's coming off, so that one's very fast. This surprised me. So these are really slow, so you don't really see too much. But then you get a really fast one, and this one accelerates all of the particles that are, in its path. So as it moves through, it's going to accelerate all of those. And we would expect it to have the composition similar to the sun. It's just accelerating particles right next to the sun. And of course, that is mostly what we see. So I got that same plot here. But in blue, I now have what we see in those energetic particle events. So mostly the same hydrogen and helium-4. Actually, helium-4 is a bit depleted. Helium-3 is actually enhanced by about a factor of 10. That's puzzling. Huh? Yeah. I could have never said that word. I wouldn't even have known. Another interesting thing, so everything else seems to agree pretty well. These energetic particle events have slightly enhanced heavy ions, so magnesium, sulfur, I don't know, and then through iron here. They're slightly enhanced. The reason for this is actually they get ionized much more easily, and so once it's ionized, it will kind of lift itself up into the upper atmosphere of the sun. And so there's actually a little bit more of it out in the outer edges of the sun. And so when that giant coronal mass ejection is sweeping through, accelerating all of those particles, there's just a little bit more of those heavier ions there. As opposed to, which one has a really, I think, helium-4 is very difficult to ionize. And that is why we see a dearth of helium-4 in these events. Okay, so nothing terribly strange here. Very similar composition to the sun. However, in the 1970s, there were a couple observations that are rather interesting related to the amount of helium-3 in some of these events. So again, this very rare isotope of helium, all of a sudden there's a lot of it in some of these events. So we see Hsieh and Simpson, God rest their soul, in 1970, were the first ones to really see, well, there's a lot of helium-3 in some of these events. And then, don't even ask me, I think India and Greece got together and made a really nice paper. That's what happened there. That's crazy. I've almost not cited this because I didn't want to have to write out those names. So you see, they saw an event in 1974 where there was more helium-3 than helium-4. That is an incredible amount of fractionation. This incredibly rare element is all of a sudden one of the most commonly seen elements in some of these events. So here, after 50 years of actually studying these events, here is what the composition of these helium-3 rich energetic particle events actually looks like. So hydrogen, pretty much the same, helium-4 about the same, and now look at helium-3. Here we're down at the other events, and then all the way up here, we see about the same amount of helium-3 and helium-4. That is quite puzzling, in my opinion. It's very hard to even make an analogy for this. The only thing I can think of is imagine you walk into a room and there's just no oxygen. It's all nitrogen, and it just happened naturally. So actually the chance of this happening by chance, I looked it up, it is about as likely as shuffling the same deck of cards in the same order 3 times in a row. So if you could do that randomly 3 times in a row, that is the chance of this happening by random chance. So clearly it is not random. Something is happening there. Another interesting thing about these events, which I won't talk about too much, but it's interesting because we have not yet solved this, is the heavy ions, again, are even more enhanced in the helium-3 rich events. So they're not only enhanced in helium-3, but also in these heavier ions. So something's going on there. We do not think that this is an ionization effect. We actually don't know what it is. I'll kind of explain all of the many different theories. Okay, so in the 70s, we saw all of this, and we asked, why is this happening? I was not alive, but other people asked why this was happening. So the first theory that was somewhat appealing was nuclear spallation. Bet you didn't know that word. I didn't know it either. I thought it was like fission. It's not fission. It's spallation. Get it right, okay? I won't, but you have to. So these are very energetic events, and so the idea is, well, if you actually have a lot of energy in the system, you might be able to break up some of these atoms. So the most common atoms, or ions, in the solar atmosphere are hydrogen, of course, there's our one proton, and helium-4. These are the two most abundant ions at the sun. If they were to run into each other with very high energy, so you need to add a lot of energy, this takes away energy from your system. If they have enough energy, they can actually, you could blow up the helium-4 and create 2 protons over here and a helium-3. So, that's one possible method. Very appealing because, again, these are very energetic events, and so it's not so uncommon that you could get this. And this happens about 50% of the time if you have hydrogen, helium, and 20 MeV. You can get this about 50% of the time. Now, the other 50% of the time, man, I forget. I made these slides like late last night, okay, so. So the other 50% of the time, if you have protons, helium-4, and 20 MeV, is you get 3H plus 2H. Now, this is not helium-3. It's also not hydrogen-3. Well, technically, it is hydrogen-3, if you wanted to call it that. But 3H and 2H are deuterium, heavy hydrogen, and tritium. Now, tritium only has about a half-life of 12 years or so. So we don't often see tritium unless it has recently been generated. So 50% of the time, we would also see this interaction. So we would expect, if we see a lot of helium-3, we should see a lot of deuterium and tritium. But it took several years to figure this out, mainly because we didn't have good detectors. We can't actually detect all of these subtleties all that easily. But eventually we got there, and we found that there was no enhancements in deuterium or tritium, and so it cannot be spallation is the reason for all of this helium-3 enhancement. And that is why this squirrel was upset. That's why I put that there, because he wanted it to be spallation. Okay, so, all right. So these were first discovered in 1970 to 1974. Now we're looking at 1992, so about 20 years later. Michael Temrin and Elon Roth. Michael Temrin has died. Elon Roth is still alive, at Berkeley, actually. They said, okay, helium-3 must be preferentially accelerated. It can't be at a greater amount beforehand. It has to be rare and then preferentially accelerated. So this is a bit of a dense slide, but bear with me here. So they are actually magnetospheric physicists. They didn't care at all about the sun. But they had observed a beam of electrons streaming into producing the northern lights. And they had observed this directly, that when these electrons were streaming in to the North Pole, the North Magnetic Pole, they were generating these left-hand circularly polarized ion cyclotron waves. Say that 5 times fast. All that is that you've got this electric field here, that's E, and this electric field is spinning around this magnetic field. So that's this omega here, it's spinning around. So that's very nice, because if you have a left-handed circularly polarized wave, that is the same direction, the left hand, that an ion gyrates around a magnetic field line. So if the frequency of the wave, omega, matches the gyro frequency of the ion, big omega, then you can get resonance, and you can actually get extremely high energy ions on the order of 1 second. Now this resonance depends, and this is what makes helium-3 unique, it depends on the charge to mass ratio. So the amount of charge is how many electrons it doesn't have. So helium always has 2 if it's fully ionized. And helium-3 has a mass of 3. So this charge to mass is 2/3, okay? No other ion in existence that lasts for more than a picosecond has a charge to mass ratio of 2/3. So this makes helium-3 very unique. So they saw that the waves generate at about the same gyro frequency of protons, okay? So that's a charge to mass of 1. Okay, it took me a moment to figure that one out. So this is the source. So the hydrogen is sourcing these waves because of the electron beam. That's complicated, don't worry about it. But if these waves travel into a region of a different magnetic field, so this B gets stronger as these waves travel, well, all of those resonant waves will move to the left, okay? To the left of this plot, starting at the source and then sinking down this way. Now look which puzzling ion is first in line to absorb all of this resonant energy. It's helium-3 right here. And notice deuterium and helium-4 are off to the left, and tritium. So we would only expect to see a very large resonance with helium-3, and helium-3 is just going to absorb all of it. It's selfish. It doesn't care about these other ions, and so it's going to get way accelerated, and all of these other ones are going to be like, hey, well, they're going to die if it's humans, but they don't eat, so they just don't get energized. Okay. So this is actually what that looks like. Literally, it spirals out of control. So you got this helium-3, it's just gyrating, and then it gets this resonant wave, and it just starts spiraling into very large, and its gyro radius becomes massive. And here was one of their plots. The y-axis is energy. I don't know why they put it up there. And this is seconds, and we see in a quarter of a second it can go from basically no energy to extremely high energy ions. So this is really where we're at in terms of how helium-3 is getting preferentially accelerated. That was at a different font when I put it in. I met Elon in 2022, and he just kept saying this. It was at helium-3 conference. Believe it or not, we all get together and talk about this thing. And this is what he said. He just kept saying, and God made helium-3. So this is where we're at. This was in 1992. There have been some new theories. All of them now rely on this resonant interaction. Almost nobody believes that it's spallation, although there's a couple people that see deuterium and they say, hey, I think that's from that. And no, it's very unlikely, statistically speaking. So that's where we are. What's my next slide? Okay, there we go. Sorry, I had to figure that one out. So what has happened since 1992? Well, we have launched very nice solar imagers into space. So really it wasn't until 1994 that we got like a dedicated solar imager, but it sucked. Okay, and then in 2006, we started to get some nice images, okay? And so this is what a helium-3 rich event actually looks like if you're looking at the sun. And I look at these all day, every day. Very exciting. So let's see, does it work? Whee! There it goes. Did you see it? If you didn't see it, I'll play it again. I guess I have no choice. There it goes. And then there's like a small one. There's a small one right after it. It's crazy. Whenever I see them, I just think it's like getting yeeted out there. Okay, so it might not be so easy to see, especially for you people in the back. So what we do is we actually take every image and we just subtract it from the one before it. It's called a difference image. And if you do that, it becomes very obvious. There it goes. I'll show one more time. Very large. So by the way, the Earth is like the size of this laser pointer. And so imagine you're in there. That's crazy. Sometimes I think, like, what would happen to me? That's insane. Okay, so here, let me freeze frame on one of those nice images there. Oh, sorry. I forgot I put that in there. Okay, so this is a freeze frame. I'd like the most energetic part. Okay. There was like dead space there. I said, what do I fill it with? So I put that dog. Okay. Very puzzling, huh? I mean, wouldn't you say? Okay, so actually there is some physics to be learned here, ladies and gentlemen. It's not so easy to see. In a couple slides, it'll actually be a little clearer. But this is not like, there's structure inside of here. So one of the most interesting things is you could see like this helical pattern. Just follow the white. So it goes down and then up and then back down and then up and then back down and then I don't know what happens in there, but nobody does actually. If you solve that, you win a lot of money, I think. So there's very structured, and it's actually helical shaped. They call these helical jets. And it's believed that there's like a strong magnetic field way down in there, and something snaps and all of it unfurls and it untwists really, and you get this helical structure here. So let me play it one more time. Boop. Nope. There we go. So it is difficult to see. You have to look at these for a long time. But there's a helical pattern in there. Very interesting stuff. Okay, so what else can we do now that we have all of these really nice images? Well, another thing which my good colleague Radoslav Buchik from Slovakia, one thing that he has been doing, which is very interesting, is if you take a bunch of images at different wavelengths of the sun, you can actually determine approximately the temperature of what it is you are looking at. And so here we see the bottom right of all of these plots, it's the approximate temperature, and the brighter, the redder you get these images, the greater the brightness at that temperature. And so he's looking at one of these sources and he sees, oh, well, it's not that bright when it's cold, it gets a little bit brighter, and then right around 1.3 to 2 million Kelvin and a little bit hotter, you really start to see this deep red, which means it's really bright at that temperature. So we can actually determine the temperature of these events, or at least we can glean the temperature of these events. And this is really helpful because the temperature determines everything, especially compositionally speaking. Why would helium-3 be preferentially accelerated at 1 million Kelvin? I don't know. But 5 million Kelvin, that might make more sense to us. So this is what he's working on with these solar imaging. Being able to see the solar source of these events is very interesting. And the second to last thing I'm going to show is something I've been working on. Another interesting thing about helium-3 rich events is that sometimes they happen one after the other very quickly, very uncommon. So here I show 6 events. This first one is very nice. Should be the clearest one you could see that helical pattern. If you could see the helical pattern there, they like to twist. It's this untwisting of the magnetic field. So here's 6 of them. The first one happened on July 15th at 7:30. And the last one happened about 24 hours later. So we saw 6 over the course of 24 hours. That's once every 6 hours. That sounds like really slow, like you could drive to Dallas in 6 hours, you know. But for the sun, nothing happens that fast, okay? It's all generally pretty slow moving over there, except for everything. So this is another very interesting thing about helium-3 rich events, is sometimes they just happen a lot in a short period of time, and we do not exactly know why that is. Okay, so I did say, is the sun running out of helium-3? I figured I'd do a back-of-the-envelope calculation. So in 2005, George Ho, my current advisor, said that a lot of helium-3 is released in each event. However, the sun contains a lot more. So it releases about 10 to the 29 helium-3 ions each event. But there are 10 to the 51 total helium-3 ions in the sun. So if one of these happened every day, which is a valid assumption, the doctor didn't find it during my prostate exam, I don't know. I thought about that one on the ride here. Okay. Yes, I'm always thinking about that next prostate exam. Okay, anyway. I'm sober, by the way. I haven't had a single beverage. It would take about 1 quintillion years for the sun to completely exhaust itself of helium-3. So to conclude, the sun is not running out of helium-3, and that cat is pleased to hear this puzzling situation resolved. Okay, thank you. What is left? I forget. Oh yeah, okay, so there's some outstanding questions. Sorry, it is my research. I have to utilize all of you people so I don't have to do any work. So feel free to answer any of these questions and let me know. Oh yeah, you're welcome for trivia, by the way. Okay. So what resonant process within these events is responsible for accelerating helium-3? Again, we know it's resonance, but we don't know exactly which resonant process. It turns out there's quite a few of them. Why do helium-3 rich events also have elevated levels of heavier ions? Is it the same process or is it totally different? So the enhancement is not too much. You have people thinking, well, it was elevated beforehand, it got elevated after the event, or it's the same exact process, just to a smaller extent. Everything under the sun. So we have no idea. What is the underlying structure of those jets? So we saw those jets. There is a lot of structure there, but it's not easy to pinpoint. And punch actually might be able to help with this. So we learned about, go punch. Do you punch people when you say that? I feel like you have to. Yeah, you punch. I don't know. So punch is able to get really more resolved images of these jets in the later stages of their life, so after they've left the sun a little bit, than we've ever seen. And so will we actually be able to see some structure there? Why do we sometimes see the repeated helium-3 rich events? Why? That is not seen with gradual events sometimes, but very rarely. But helium-3 rich events, you just see one after the other, like it's, I don't know, a semi-automatic rifle or something like that. And then last, why are people trying to extract helium-3 from the moon? Nobody has actually explained that to me, but apparently people are doing it, and they even make Hollywood films about it. Caleb, I don't actually want to hear an answer. I just want to be angry. Okay. Thank you very much. That concludes my presentation. Thank you. Okay. I assume no questions. I've explained everything perfectly.
Yeah, no questions. Not a single person said the same thing. Put the helium-3 in the bag. All right, first question. Does the sun store helium-3 for the winter?
What kind of question is that, guys? Come on.
Because the squirrels.
What? That means you just made it up, or maybe not.
Of course I made it up. Oh, can you go to the next slide?
The next slide? Oh, yeah, okay, there we go.
What would happen if the sun did in fact run out of helium-3?
Nothing.
Wait, can it run out of helium-3, or does it
Man,
produce
if we ran out of helium-3 right now, I don't even think we would know. Although, actually, I'd be like, I would publish a paper, where did all the helium-3 go?
The next clipping title.
Yes, yeah. This would be the evolution of helium-3 rich events. Now they're helium-3 poor helium-3 rich events. If I could put a squirrel in my paper. They won't even let you put an exclamation point in a paper. Isn't that absurd? I once put an exclamation, and then one of my co-authors was like, what is this? Emotion? No.
You got to come up with some kind of satellite that's a squirrel.
Also, the naming convention nowadays is crazy. Punch is actually pretty good. Polarimeter to unify, I don't know, you even put the U in the end there, the corona and the heliosphere. I mean, it's pretty good, but man, some of these are terrible. You just look up serpentine. What does that even mean? And it doesn't mean anything, sorry. But squirrel would be a cool name for a spacecraft is what I'm trying to say.
In your plots, why are they relative to oxygen?
That is a good question. So why do we make all of our plots relative to oxygen? One reason is statistics. We actually see a lot of oxygen, and so we can normalize to it. If you normalize to some low count piece of crap ion like sulfur, then you would get crazy ratios because sometimes you just don't see a lot of sulfur. So we normalize to oxygen there. Other than that, I think it's convention. People actually just started normalizing to oxygen in the 60s, and we just didn't stop.
Pedantic question. Do you see a lot, or are the detectors favored towards seeing oxygen?
No, the oxygen is definitely, if I go, oh my goodness gracious, you guys
Wrong
didn't
direction.
see those. Where are we? Here we go. Oxygen is, as far as the sun is considered as well, the fourth most abundant ion in the sun. So there is a lot of oxygen.
Can you go back to the question slide? Send your questions in if you got them. Sam answered them all, apparently.
I'm done, actually, if you want to.
My question,
Just kidding.
How was
Bring 'em
helium-3 detected in the 70s? How did they originally see that?
Oh, man, I don't even know. So the biggest issue is that helium-3 just looks too much like helium-4. And so you need to be able to know the exact speed that the particle has come in. So you got to get its time of flight. And you need to know the exact energy, and that's deposited when it runs into the back of your detector. And so with E and V, you can get mass through the kinetic energy equation. That is generally how they do it. Maybe back in those days, so they looked at higher energies. Oh man, if anyone, what? Are you, what do you, the thinking guy? What's the next slide? Oh, okay. Oh, I'm sorry. Okay.
Thank you, Brittany.
Great, now I'm confused. Oh, yes, yeah. So the original detections, so this is what's interesting, is the original detections were at much higher energies, and so they didn't see them, helium-3 rich events, even though they happen all the time. They thought they were incredibly rare because they just don't reach that high of energies. And so they were looking way too high, and all the events are happening down here. So they used actually what's called a DE-DXE detector. That is so boring, you guys don't even want to know about it.
Abdullah asked if he can show the hidden slides.
Hidden slides? Oh.
Next is trivia, so.
I have no hidden slides. What? No, I showed every single
You
slide.
got the memes?
All right.
Last question.
Oh.
This is courtesy of all of the grad students. Why are you like this?
Sorry, I get excited about a rare isotope.
And so you think of squirrels?
No, I did that for my wife. Yeah, that's true.
Yeah.
She sends me those images all the time. She doesn't have emotions. She uses squirrels to emote
No one
her.
proofread these slides?
No, actually, courtesy to Brittany, I probably practice every single talk to her about 20 plus times. I don't come out here, except for this one. Yes, so this one, I'm totally improvising, except for the prostate exam joke, which I thought of on the way here.
Why was that not the on improvise? Let's take our speaker, everyone. Thank you.
Yeah, thank you. Thank you, thank
All right.
Oh, perfect timing. We're at 8:30, so if anybody has to go, we thank you for coming. We hope you join us again for our next AOT, the first Wednesday of August, which will be the number 6th, August 6th, Wednesday, August 6th. Yours truly will be presenting at that AOT, so you better be there, or I'll find. No.
2 UTSA grads.
Oh, who
By
el-
that point.
Who else?
Adolfo.
Oh, right. Yes, a former speaker and a former student, Adolfo Santa Fe Dueñas, will be there as well. So, exciting talks. But if you can stay and stick around for trivia, we'll get it started in roughly 5-ish minutes. We'll go ahead at 8:35, we'll say. Remember, max group size of 4. So if y'all are larger than 4, split off into multiple groups. And we will come around with the sheets and writing utensils.
You got good odds. Oh, I thought you got one.
I got one, but then Brittany took it.
All right, let's get this show on the road.
All right. Question 1. Russian etymology. Did you know? Question mark. Sputnik is actually just the Russian word for satellite. The name derives from the prefix. That's a letter. The name derives from the prefix S and the word Putnik, which combined means Sputnik. I find it hard to believe that a letter counts as a prefix.
Yeah, like
I guess.
atypical,
I guess that's
abnormal.
is that Greek or Latin?
Yes. Sputnik. Ah, shoot.
You do the loop and pull, and your shoes are looking cool.
Bum bum.
All right, everybody good?
All right, question 2. Can always come back if you need it. Dapper Dan, this lesser-known physicist, pictured here, is responsible for patenting the coaxial cable, deriving an analytical form for the step function, and consolidating Maxwell's 12 equations down to the now infamous 4 equations. Is it A, George Gamow, B, Oliver Heaviside, C, Edwin Hall, D, Irving Langmuir, or E, Michio Kaku?
Michio Kaku. this unknown physicist, Michio Kaku. Once it said step function, I was like, oh, okay, I know who that is. He? All right, everybody good? Question 3. Name that celestial object. This slightly edited image shows which well-known object in the X-ray spectrum? A, the Ring Nebula, B, Eta Carina, C, the Crab Nebula, D, Lagoon Nebula, or E, Michio Kaku.
I think it's Michio Kaku. I mean, that's what he looks like.
I mean, you got the gray, wispy hair. I don't think this is a hint because I'm not saying the name. Well, I can talk about it at the end.
I will say this is very pretty. This is X-ray, so that's
It looks much better on my laptop.
yeah. Well, yeah.
You can't see the purple.
Projectors aren't. The X-ray is, of course, shorter wavelength. Than the even ultraviolet, right? So this is deep, fast pulse, and,
High
and
energy.
we hope high energy. We hope to have an X-ray talk coming up soon from a UTSA professor who gave an X-ray talk last year. If any of you remember Eric Schlegel's talk, he talked about the well,
Third time's the charm.
yeah, the third time's a charm with the Chrism instrument, and I'm happy to say that when he gave the talk, it wasn't up there. Now it's up there, and it's taking good data. It actually works. Third time really was a charm, so we want to get him back to talk about it. So that's a little aside on X-ray spectra, which doesn't get a lot of love, especially right now. The poor Chandra X-ray Observatory. No, I know, but the Chandra X-ray Observatory is suffering right now. It works fine. It's still taking beautiful pictures. All it just needs is support, and it doesn't have any support right now. So it needs support. As does Hubble, by the way. Hubble's not looking good. But question 4. Well, planned deorbiting. How many Starlink satellites are currently in orbit and operational? That's the operative word. That was a pun. Is it A, 1, B, 24, C, 144, D, 892, or E, 7,855? The bonus, which we want you to write the bonus for this one next to the letter that you choose. How many have been deorbited, either planned or otherwise? And the closest answer will be awarded a half a point. So,
If it's planned, has
how
it been
many
deorbited?
of you in this room have seen a
Oh, I see what you're saying. I see.
train in the sky? Remember a big, yeah, they're very freaky.
The trains are so freaking weird. So unnatural.
You first see a smudge. You think you're seeing things. You think your eyes are malfunctioning or something. You see just a giant smudge in the sky, and then as they go higher toward the apex of the sky, you can start to see individual dots, and you realize what exactly you're seeing, and it's a collection of satellites. Really? Could have been.
All right. Everybody good? Question 5. The penultimate frontier. This body of water lying between the southernmost tip of South America and Antarctica goes by what name? A, the Drake Passage, B, the Strait of Magellan, C, the Bering Strait, D, the Great Belt, or E, Michiokaku? No, E, the Minch.
You know this one, right?
Yeah.
All right.
Planned.
The sixth question, which we'll get up for you in a minute, which will be about mythical constellations. But what else can I do, Sam? We have.
Talk about your prostate.
It will what?
Talk about your prostate.
Oh God. Oh here no. No. One more. All right. In this popular novel series, the Ship, Hammer, and Leopard constellations are sequentially named by a star-loving character. Is it A, The Hunger Games, B, The Lord of the Rings, C, Harry Potter, D, The Chronicles of Narnia, or E, A Song of Ice and Fire?
All right, does anybody need a question repeated? Hold your fingers up if you need a question repeated.
1 through 6. We good?
All right. Time for the bonus. You can really appreciate the background with this. Regarded, this goes in the bonus section of the trivia sheet. Regarded as the most intelligent photo ever taken, this photo was taken at a quantum theory conference. This photo was taken at a quantum theory conference. Of the 29 attendees, 17 now hold Nobel Prizes. What is the name of this conference? And what year was this photo taken? Each answer is worth 1 point. If you know what it is and you don't know how to spell it, because I don't know how to spell it in a way that when we read it, we know what you're saying. It'd be hard to not do that.
Yes, and when you're done, bring your sheet up and your writing utensil if we gave one to you. Please give us back our pens.
Please do.
Good for her.
All right, Sam, you were okay. So there's Bohr. I think that might be Michelson. There's Pauli. De Broglie. Dirac. Schrodinger. That's Aaron Schrodinger. Yep. Marie Curie. And that might be Becquerel there. That's Max Born? Okay, yep. And of course, Einstein. Everybody can recognize him from a mile away. There's Heisenberg. That's Heisenberg. Yep. Let's see. I'm wondering if that's Rutherford. I don't think so. Yeah. Middle right, that's Bohr. Heisenberg's right there. Is Compton anywhere in there? Oh, he was pretty early on. Honestly, that might be him. Maybe? No. Yeah, well, we'll have to look up who everybody is, but
All right. We're going to get to the answers, but I want to let you all know that the highest multiple choice, at least, score was 4, except for the hosts. We're not in the trivia.
We're not in the running.
We're not in the running to win anything, but we got 5, so we just wanted to let you all know that.
Michael wanted to brag.
Yeah,
This is a rare occurrence.
All right. Start us out.
Answers. Question 1. What? The prefix of a letter. Fellow traveler. The name derives from the prefix S and the word Putnik, which combined means fellow traveler. Actually, I realized I didn't read the answers. I didn't even know space potato was one of them.
All right. The coaxial cable was made by Oliver Heaviside. And for the physicist out there, no physicist should have gotten this wrong. And I'll tell you why. Because the Heaviside step function.
I thought about that, but the coaxial cable thing threw me off.
But the Heaviside step function. The what? All right, there you go.
Why did the coax cable throw you off? I feel like also for like electrical engineers and like probably the Heaviside function is probably used in a lot of things. Anyways, name that celestial object, Crab Nebula. What I was gonna say, and then I didn't say because I don't know if it'd be a hint. This is one of the few imaged objects where you can see the light echoes emanate through the observations. You can watch a wave of light propagate away from the central pulsar, I believe.
Yes.
Yeah.
You can also watch the jet stream.
Oh yeah, go out.
There's a movie version of this data from Chandra. Yeah, so this is data from Chandra, and there is actually a movie version of it where you can watch not only the light echo, but also the jet evolve over time in a little movie. So I highly recommend you do that because it's really cool.
Not many celestial objects you can watch in human time.
Nope, that's for sure. All right, the orbiting of the Starlink. Well, first of all, the operational Starlink, the answer is E, 7,855.
And we're only just getting started, apparently.
And 523 have fallen back to Earth. So that means
So
the
says Sam.
total launched have been 8,378. Which is a lot of satellites to launch. We better, listen, they better get that darn, what's that big one again? The Starship?
Starship.
They better get that working, because you know how much money it is to launch each one of these individually without a big super one? They got to get it working.
Well, they launch them.
Well, yeah. But they got to, I mean, but these little rockets are very inefficient at launching these types of things. They got to get that big
one. They launch a lot
one.
of them at once.
Yeah, but not enough.
Sure,
Not
yeah,
enough.
not enough, yeah.
Not enough.
Name that passage. Wait, right? No. Yeah, name that passage. Drake Passage. In between. Oh, picture changed.
And-
in between Antarctica and South America.
And
it
if
is- go ahead.
If you chose B, I can understand why, because
Go ahead.
if you chose B, I can understand why, because I at first was confused. But you see where that dot is that says Punta Arenas? That is the Strait of Magellan, up there. The whole passage of the ocean is Drake's Passage. The Strait of Magellan is just that little strip of water up there.
No, we're talking about this. It's a map of the Drake Passage. It seems like some kind of geologic map, because it's like all the stuff underwater. Yeah. Oh yeah.
Yeah.
Where two oceans meet.
Yeah, the swirlies are funny. They do. All right. The final question of the multiple choice portion was about that mythical constellation. So we had the ship, Hammer, and Cougar. And the answer was D, Chronicles of Narnia.
No idea up here.
I'm sorry, Leopard, not Cougar. Close enough.
Same.
The Chronicles of Narnia. Sam, do you know which book this was from? Yeah. Okay. That's why I think I only read The Lion, the Witch, and the Wardrobe.
I didn't read any of them.
Yeah. All right, bonus.
The proper bonus. Name that conference. Solvay Conference, 1927. I was very surprised. A lot of people knew the year. I knew the name. I didn't know the. We kind of guessed, but we got it right, surprisingly.
All right. Now that we've gone through all the answers, we've got winners. And Aaron is grabbing the third place prize tonight. It is a PDS, which stands for Planetary Data System, tote bag, as well as some stickers, including the SWIPS, which is the solar wind and solar wind plasma sensor, and the punch mission that was discussed. You'll get a little sticker here. And the winner of third place prize is Squirrel. Woo!
I didn't prepare. I'm just kidding.
All right, our second place winners will also win the SWIP stickers, but this time a big punch sticker. Look at that. And a Celestron Frisbee, which is perfect for the summer. And it glows in the dark, so you can bring it to South Llano. The winner of second place is Happy Face. Just a little happy face. Woo. Good job. All right. The top prize tonight is a 3D puzzle. It's puzzling.
It has instructions.
Of the space shuttle. It claims with easy instructions. So I don't know whoever the winner is. I hope you're a regular, so that next month you can tell me how easy it was. And once again, SWIPS and the big punch sticker. The winner tonight, drum roll please. The 4 Idiots. And I can confirm
Can't confirm.
Oh my God. Hell yes. We thought we did horrible.
Congratulations to our first place winners. Y'all have to let us know about how that building goes. You can put it. You guys can put it in your apartment.
Oh yeah. Oh yeah, you're
Yes, at least. All right. Flip us to the next slide. We'll end off tonight with a very heartfelt thank you for joining us this evening. I know the weather wasn't great, traffic wasn't great, but thank you for sticking it out and joining us. We'll see you next time on August 6th, Wednesday. Special thanks, of course, to Blue Star for hosting us every month, UTSA and Swery for their continued support, and be sure to follow us on our socials and sign up for our email list if you're interested in returning to our many fun events here at AOT.